And now for the dramatic conclusion of Unit 7. Write the equation for the dissolution of lead to carbonate. That's going to be PbCO3 solid is in equilibrium with Pb plus 2 plus CO3, 2 minus. Calculate the molar solubility of lead 2 carbonate in pure water. Got a little ice table set up over here. So I'm going to have Pb plus 2 and CO3, 2 minus. Initial, 0, 0, because nothing has dissolved yet. Plus x, x, x. So this means that our K equation is going to be 7.4 times 10 to the negative 14th equals x squared. Take the square root, and you get 2.7 times 10 to the negative 7th equals x. So that's the answer. How do I know that? Well, it's a 1-to-1 ratio, so if this is 2.7, that's 2.7. What about lead 2 carbonate when added to 0.7 molar Na2CO3? So this one is going to be just a little bit different. So same equation, so I'm not going to write it out again. So I'm going to have Pb plus 2, there's a common ion here. I'm going to have CO3, 2 minus, still 0, but now I've got 0.7 molar to start with from the Na2CO3. So plus x, so I have x and then x plus 0.7. So now I'm going to have something different, and I'm going to have 7.4 times 10 to the negative 14th equal to x times x plus 0.7. But here's the thing, K is small, so this x is going to 0. So that means that 7.4 times 10 to the negative 14th equals 0.7x. So we shall divide 7.4 negative 14 divided by 0.7. So I get 1.06 times 10 to the negative 13th. 1.06 times 10 to the negative 13th equals x. Does that make sense? So this is saying that it has become less soluble. Well, that makes sense, because if you add in a common ion, it's going to shift it back to the left. Calculate the percent decrease in molar solubility from pure water to Na2. Okay, well, that's silly. I guess we're going to do, I don't know, the big one minus the small one. It's kind of like percent error, I guess. So I guess we'll do 2.7 times 10 to the negative 7th minus 1.06 times 10 to the negative 13th divided by my original, which was 2.7 times 10 to the negative 7th. That whole thing would be times 100. So that's weird. So if I do that, what's my percent decrease? Oh snap, that's a big number. So it's kind of like percent error. It's 99.9% decrease, which is a huge decrease, which is saying it's almost insoluble once you add in the Na2CO3, which makes sense. That's real small. Okay, you now have a solution of Pb plus 2 with that much molar, and CO3 with that much molar. Will it precipitate form? Justify your answer using the knowledge of KSP. So, no, it won't. How do I know? Well, my KSP is 7.4 times 10 to the negative 14th. So if KSP is 7.4 times 10 to the negative 14th, my Q equation would be those multiplied together. So it would be 1.67 times 10 to the negative second times 6.67 times 10 to the negative second. If we multiply those together, so 1.67 e negative 2 times 6.67 e negative 2, that gives me 0.0011, or 1.1 times 10 to the negative third. So Q equals 1.1 times 10 to the negative third. This means that Q is less than K. Oh no, that's wrong. Q is greater than K. Negative 3 is bigger than that. Q is greater than K, which means it's going to shift to the left. And I don't even remember what the original question was. Will it precipitate form? Yeah. Yes. Precipitate forms. Because my solid is on the left. Okay. pH and solubility, given the following information. Equation. Would strontium fluoride dissolve more readily in 1 molar HCl or 1 molar NaOH? So 1 molar HCl or 1 molar NaOH. So what is going to drive this more to the right is what it's asking. So if I add in HCl, to strontium fluoride, the HCl is going to react, the hydrogen is going to react with the F, which is going to take away reactant, which is going to shift it to the right. NaOH would react with the SR. NaOH would react with the SR. With SR. But it's not a 1-to-1. I have double the amount of F that could react with the H. So the answer is going to be HCl. It's going to be HCl because the H plus will react with F minus, causing shift to the right. Calcium hydroxide was added to solutions with different pHs and the concentration of Ca plus 2 was measured. Given the data in the table to the right, what is the relationship between pH and the concentration of Ca plus 2? Okay, we're good at reading tables. So pH goes up, Ca goes... I can't even see the whole table, that's kind of annoying. As pH is going up, it looks like my Ca is going, it's getting smaller. Yeah, so the relationship is, as pH goes up, my Ca plus 2 concentration is going down. Why? Why is this a relationship? Well, you would have more OH. I would have more OH minus, and if I have more OH minus, CaOH2 breaks up an OH minus, which means they have more products, shifting it back to the left. So if it shifts back to the left, then I'm going to have less. So therefore the pH is going to increase. More OH minus, shifts left. So pH increases. Last page. Almost last page. Zinc hydroxide is a relatively insoluble salt. How would the system be affected by the addition of a strong acid? Will zinc hydroxide, ZnOH2, is going to break up into Zn plus 2 OH minus. If I add HCl, the H is going to react with the OH, reducing that, which means it's going to shift towards the side that I remove stuff from. So it's going to shift right. And if it shifts right, my solubility is going to increase because it shifts to the side where you remove products. Okay, that was easy. The change in heat of reaction is indicated by the symbol delta H. Another factor is delta S, which is a measure in the change of entropy, or I guess you could say disorder, of a system. If delta H is negative positive and the delta S is negative, then the reaction is favored. So we usually want delta H to be negative because we want a negative number, and we want delta S to be positive because a negative minus a positive is more negative. Below are the KSP values of the hypothetical salts in water at 25 degrees Celsius. So this is the least soluble, that's the most soluble. Which value goes with each salt? Strong bond between A and B. Strong bond between A and B. That means it's probably not going to dissolve well. So this is going to be the KSP 8.6 times 10 to the negative 14th. Weak bond between C and D. C and D have a strong attraction to water molecules. So this is going to be the biggest KSP. So the KSP where it's 2.4 times 10 to the negative 4th. Strong bond between E and F. E and F ions have a strong attraction for water molecules. So here they had a strong bond and little attraction. Here they have a strong bond, but they do also have some attraction to water molecules. So this one's going to be the one in the middle. So KSP is 7.1 times 10 to the negative 9th. Order the hypothetical salts in soluble least to most. From most to least. So most is CD. The middle one is EF. And the least is AB. Which salt most likely has the lowest delta H value? Probably CD. Because CD will easily dissolve. The lowest entropy value, that's probably going to be AB. Because AB does not want to dissolve. It wants to stay in that solid form. And that was Unit 7. Okay, bye.